Hello, in this video we are going to talk about the Faraday's law of electromagnetic induction. Expressed in mathematics, this is what the law looks like. E is equals to negative d phi dt. E refers to the induced EMF in this coil. Phi refers to the flux linkage of this coil. So what the law says is that whenever the flux linkage of this coil changes, there's going to be an EMF induced around this coil. The magnitude of the induced EMF depends on how fast the flux linkage is changing. As for the direction of the induced EMF, that's where the negative sign comes in. The direction of the induced EMF is always opposite to the direction of the flux change. So how did Faraday come to this conclusion that E is equal to negative d phi dt? Well, the law must be based on some experimental observations, right? So this one here is not exactly the experiment that Faraday did, but it illustrates the same observations. So I'm going to use this to explain. Now see, there's a light bulb here. It's not lighted up because it's connected to just a coil of wire. There's no battery, no EMF, so it's not lighted up. But I have a magnet here. So see what happens when I move the magnet. You see it light up? Now let me move it away. Bring it closer. Move it away. Now notice that if I move it faster, it'll light up more strongly. But if I move it slowly, it doesn't light up that much. Then the other thing is, when it's not moving, then it's not lighted up. It lights up only when the magnet is moving. And one more thing, if I put a voltmeter here, you can see that the direction of the induced EMF is different on the way in and on the way out. Why is that so? Let me introduce you to this guy here. He's an extreme weight watcher. He's always weighing himself and checking his own weight. The funny thing about this guy is, he's not worried if he's 200 kilograms. And he's not worried if he's 20 kilograms. He's worried only when his weight changes. So when his weight is going up, he worries about obesity and everything, and then he tries to oppose this change by eating less. But when his weight drops, he's worried that he's getting malnutrition. So what does he do? He tries to arrest this trend by eating more. So the coil has a similar problem. The coil is always watching. Watching what? Watching its magnetic flux linkage. So whenever the flux linkage changes, he gets worried and he tries to do something. And his reaction shows up in an induced EMF. And the direction of the EMF is always to try to oppose the change. So let's go back to the magnet thing. So why does moving the magnet results in an induced EMF? Now, do you realize that the magnetic flux linkage depends on the distance between the magnet and the coil? So when the magnet is far away, the flux linkage is small. But if the pole of the magnet is very near the coil, then the flux linkage is large. You can literally count the number of few lines passing through the coil. You can see that the amount of flux captured by this coil here is much larger than the flux captured by this coil here. That explains why there's an induced EMF when the coil is moving nearer or further away. In fact, the faster you move the magnet, the larger the induced EMF, because the rate of change of flux linkage is faster. But there's still one more question. What about the direction of the induced EMF? Okay, let's talk about the scenario when the magnet is moving towards the coil. What does the coil experience? It experiences an increasing leftward flux. The coil can have an induced EMF in two directions, either this way or this way. So which one does the coil do? Now remember, the change is an increasing leftward flux. If the induced EMF results in an induced current that produces flux that's also leftward, then that's not opposing the change, right? So to oppose the change, the induced EMF should be to produce an induced current that produces an induced flux that's rightward. So bring in your right hand grip rule. You want a rightward magnetic flux, which means the current should be flowing this way. Yeah, if you look from the right, it's an anti-clockwise current. It's so that you produce a rightward flux, because the increasing external flux must be opposed by an induced flux in the opposite direction. Okay, how about when the magnet is moving away? So if the magnet is moving away, the coil is experiencing a decreasing leftward flux. Decreasing. So what should the coil do? Should it produce flux that's leftward or rightward? Because the leftward flux is already decreasing. If you produce a rightward flux, you make the leftward flux decrease even more. So to oppose the change, what we need is a leftward flux to kind of like support, to kind of like give this leftward flux some support. So to produce a leftward flux, use your right hand grip rule. You want to produce a leftward flux, so your thumb points leftward. So your fingers tell us we need a current that is clockwise. If you look from the right, counterclockwise, because only then you can produce a leftward flux. So when the change is caused by a decreasing external flux, the induced EMF will be such that it tries to produce an induced flux in the same direction. So now do you understand everything that you saw in the applet? Do you understand why the bulb was brighter when the movement is faster? Because when it's faster, d phi dt is larger, right? The rate of change of flux linkage is faster. Then do you understand why the induced EMF is one way when the magnet moves in and the other way when the magnet moves out? Because the induced EMF always tries to oppose the direction of the change. It depends on whether the change is an increasing flux linkage or decreasing flux linkage. Alright, that's all. Ta-ta!